So today we'll be discussing some problem related to rank theorem. So and some problem with linear maps mainly. Okay, so let me recall what is rank theorem says. So the assumption on the vector space. So again I'll start with let V be a finite dimensional. So for the rank theorem we need actually the one V vector space is finite dimensional. The finite dimensional vector space over a field K and W be any vector space over the same field. Over K. Okay, and suppose we have a map, a linear map. Suppose A from V to W is a linear map. So whenever we have a linear map between these two vector spaces V and W, such that V is finite dimensional, then we have the following, that rank of F plus actually nullity, I will say, like nullity of, I'll define what like how rank F and nullity F is defined. So this is exactly will be dimension of V over the field K. Okay, where rank F equal to nothing but the, so whenever you have a linear map from V to W, image of F will be again a subspace of W. So and that is over same field K. So I can talk about the dimension of that thing, because the dimension of V is finite, so dimension of image F will be also finite. That you have probably seen, or just take that like simple thing. So rank of F is nothing but dimension of image of image of F. That means FV, dimension of K. So that means dimension of F of V, the whole image. Because V is finite dimensional, that's why I can define this FV. FV is also will be finite dimensional subspace of this W, and there I can take just dimension. And nullity, what is nullity? Nullity of F, this is nothing but again kernel of, I can also talk about the kernel of this map, which is all vectors that maps to 0 in W. So that is kernel of F, and that is again a subspace of V, and V being finite dimensional, any subspace of V again will be finite dimensional. So there also I can talk about the dimension of F, kernel of F. So this is the nullity of definition of nullity. So both this is finite, dimension of V is finite, also this sum makes sense. So that's how this is called the rank theorem. So the whole setting, this is the rank theorem. Okay, so let's first see some simpler example. Not exactly that about the rank theorem, but something related to just linear maps. So when you have a finite dimensional vector space V over field K, and UW2 subspace of V of same dimension. Then you need to find a linear map from V to V. Sometimes it is called endomorphism. So any like endomorphism are linear maps from same space to same space. So this is so F is a endomorphism you have to find such that F maps U onto the W. So image of F U will be totally of W. So V is finite dimensional, so and UW being subspace, they are also finite dimensional and they are of same dimension. So you can use like basis and can find F easily. So do you have any like idea how to do this one? Okay, so let me just so V is finite dimensional and UW are also equal dimension. So I can take a basis this one of U and a basis of W, say W1 W2 again Wm of W. Now we need to like to define a linear map from V to V, enough to define it on a basis and extend it linearly, right? So so as I want my image of U should be totally of W, so I should define my F such that F of Ui equal to Wi. Then it will be totally like it takes the basis to basis, so and so image of U will be exactly equal to W. But I need to define also elsewhere also, because U may be just a proper subset of V. So to define that I need to extend this basis to a basis of V, right? So then extend the basis U1 up to Um to a basis. Say your like dimension of V is M plus N, so let's say U1 up to M plus N, okay? Basis ato of V for like any for some n greater equal to 0 or n greater equal to 0 some, okay? Now I can define, like I'm ready to define a linear map from V to V. So define A from V to V by, I'll just define on this basis of V, right? Then I can extend by F of Ui equal to Wi for like 1 less equal to I less equal to M, because that is exactly the basis of U, so I should send that to a basis of W. So this is Wi, and elsewhere I'll just put 0 for like M plus 1 less equal to I less equal to M plus N. Then clearly, and I defined on this basis and extend linearly. On whole of V, because any vector is a linear combination of U1 through Um plus N, so I can use the like linearly I can just define F, okay? So hence F belongs to like endomorphism, set of all endomorphism is denoted by end of V over K, and and f of u is exactly w, right? Because this basis goes to this basis. Hence, this is an existence of an endomorphism, required endomorphism. I hope this is fine. So it is just the extension of basis and define the linear map on that basis. Similar question, we have another one, like if you have a finite dimensional vector space over field K, and like if you have a subspace of V, then you can actually define an endomorphism of V such that kernel of F is exactly U. So previously you had like two subspace U and W, and one is exactly mapped to other by an endomorphism. Here we are saying that for any subspace you can actually construct an endomorphism whose kernel is exactly that subspace. Okay, so again you can proceed just similarly, like instead of like two bases, you can just start with take a basis um of u and extend it to a basis u1 up to um plus 1 up to um plus n, again of v for like n greater equal to 0. Okay, so this is your basis of v. Now we can define exactly like u is spanned by this u1 through um. So I should, as it should belongs to the kernel of f. So whatever f I should define, that should consist of all like that, all of that, like that map should send this u1 to um to 0, so that u is contained in kernel f. And if I take the other vectors, just send it identically to other vectors, then the kernel clearly will be exactly u. So I can define simply just this map, that define f b to b by f of ui equal to 0 for all these vectors 1 to m. So 1 less equal to I less equal to m, and elsewhere it is just identically ui, because I don't want anything else to lie in this kernel of f. So m plus 1 less equal to I less equal to m plus n, right? So then clearly, as on the and extend linearly, obviously this I only defined on the basis, but to define on v you must extend it linearly. Then we have kernel of, so all these, then ui belongs to kernel f for 1 less equal to I equal to m. This means u also contained in kernel f, but nothing else is also contained in kernel f, because like if some v belongs to like kernel f minus this subspace u, then I can write that as like, okay, so let me just do it other way, that to show exactly kernel of f is u, so let v belongs to kernel f, and kernel f is a subspace of v, so I can, so v I can write as sum of ci ui for 1 I equal to 1 to m plus n, and Ci belongs to K. Okay, so then kernel F belongs, so this f of b should be 0. F of b is 0, that means this sum Ci f uy, this I equal to 1 to m plus n, this is 0. But by definition of our thing, this is just simply sum of I equal to m plus 1 to m plus n Ci f uy, right? So just a minute. Okay, so this is 0, but this is 0 means I can again like just take back all the thing, and so this actually imply that okay, this sum of I equal to m plus 1 to m plus n Ci uy, this, okay, just a minute. So this actually 0, I should show that all this Ci equal to 0, right? Then I can say that this m plus 1 to m plus n, these are 0, then it is clearly belongs to m plus n. But okay, okay, this is belongs to kernel of f. So this belongs to kernel of f, but this is a like okay, so this is just that thing. F of uy again on the this side, it is again by definition this is Ci uy, right? Because on m plus 1 through m plus n, this is just Ci uy. But being a basis u1 through um plus n, this being a basis, so any subset of it is again a basis. So in particular linearly independent, and you are taking a linear combination of those vectors that equals to 0. So by linearly independence, I must have Ci equal to 0 for m plus 1 less equal to I less equal to m plus n, right? So once you have this one, then you clearly V is just the linear. So this implies V equal to sum of I equal to 1 to m Ci uy, because others just equals to 0, and this is clearly belongs to u, because it is just a linear combination of the basis element. So I took an element V from kernel F and showed it in U. So kernel F is again contained in U, hence so this implies actually hence kernel F exactly equals to U. Okay, so this implies kernel F contained in U, and combining this with that, we get the required thing, right? Okay, I hope this is also fine. Nothing like we haven't used much of this one. And next we will have this one. So in this case we will actually use the again like isomorphism property. So equivalent condition for the isomorphism, and not isomorphism, rather non-isomorphism. So again you have V a finite dimensional vector space over field K, and F is an endomorphism of V. Then we need to show the following two conditions, and here also you have another three conditions. So these all three 5 property actually statements saying the same thing. So first one is, if F is not an automorphism of V, that means F is already a endomorphism. Not automorphism means it is not isomorphism. So not isomorphism means, again, like by rank nullity theorem, you know that it is not injective and not surjective also. because if it is injective, then it automatically implies that it is also surjective by rank nullity theorem, again like the rank theorem. Similarly, if you have this is surjective, then that also again imply that this is injective. So first of all, let me just a remark first that so f is not an automorphism. So that like implies by that as f is already an endomorphism, so we must have f is not bijective, and due to again rank nullity that this is same as f is not injective as well as surjective. Why that? Because by rank theorem I know that if f is injective, then the dimension of kernel of f is 0. So rank f plus nullity of f equal to dimension of v. So if f is injective, we know that f is injective if and only if so as f is injective if and only if kernel of f equal to only consist of only 0 vector, then and that means that nullity of f is 0. But nullity of due to this rank theorem, nullity of f is 0 if and only if rank of f equal to dimension of v, right? But rank of f is again a subspace of v, and image not rank of f, image of f is a subspace of v, and that subspace has dimension exactly equal to v, so it must be equal to exactly v. So image of f, that means f of v is whole of v. So that precisely imply that f is surjective, right? F is surjective. So that's why we get like that injective and surjective thing as this thing, okay? So we need to use that thing to like show the existence of such endomorphism with this relation. But 2 if and only if 2 prime, this is easy to see, because once you have g not equal to 0 such that g compose f is 0, then existence of g prime not equal to identity is like you just take g prime to be identity of v minus g, then g prime compose f will be like f minus g compose f, and g compose f is 0 by previous thing, so you have that exactly g compose f, g prime compose f equal to f. So let me do that first. So first 2 implies 2 prime, let's say. Let's do that. Okay, so 2 if and only if 2 prime, so if g not equal to 0, 0 means the like sends every vector of v to just 0, so 0 of v such that so there exists g belongs to g compose f equal to 0, so again 0 of v. So then you take G prime equal to just identity of V minus G. This is again a linear map, and this is not identically equal to identity of V because G is not equal to 0 of V. So this is not equal to 0, not equal to identity V, and G prime compose F equal to, so identity V minus G compose with F. Identity V compose F is nothing but F. So this is F minus G compose F, and G compose F is 0, so this is just F. And similarly, like converse also, 2 and 2 prime you exactly define in the same way. Like if you have G prime, there is this G prime not equal to identity of V such that G prime compose with F equal to F, then define G equal to same thing, just identity of V minus G prime. This is not equal to 0 because G prime not equal to identity V. So 0. Then G compose F is F minus G prime compose F. G prime compose F is F, so F minus F. So this is 0. So 2 implies 2 prime is easy. Let us show now 1 implies 2. Okay, so 1 implies 2. So it is not an automorphism of V. So let us suppose that F is not surjective. Okay, and V is also finite dimensional, so not surjective. That means image of F is a proper subspace. So image of F is a proper subspace of V. So suppose image of F is spanned by image of F equal to let me, so V, let just V1 up to Vm be a basis of this subspace image of F, and it extends to a basis V1 up to Vm plus n, and here in this case n must be as this is a proper subspace of V, so n must be at least greater or equal to 1. Okay, in this case, and then you can define your G, because you want your G compose F to be 0, right? G compose F to be 0. So F, so I should define the where F is not taking 0, like on the V1 to Vm, F is already 0. So this thing is already 0, but where F is not taking 0, there I should define my G to be 0, right? So and okay, so this is my image of F. I extended that to a basis of this thing. So define G from V to V by G of Vi equal to this Vi already span your image of F. So this Vi I should define that to be 0 for 1 less equal to I less equal to M. and otherwise I can just take anything m plus 1 through m, that is already not a part of your image, so that already goes to 0. So there I can define like vi, simply vi, to maintain that this g is non-zero, because n is greater or equal to 0, so at least one vector should be there, and that guarantees that g is not identically 0. n plus n, as n greater or equal to 1, so g is not equal to just the 0 map. Also g compose f of any v, this is 0, as fv belongs to image of f, and that is spanned by, so this is my notation for span, that v1 through vm, this is spanned by v1 to vm, right? So as this is this, and this is true for all v belongs to v, so this g compose f equal to, that means g compose f equal to 0, identically 0. Okay, so converse also a similarly we can do. So for the converse thing, that if you have so there exists g from v to v such that g compose f equal to 0 v, and g is non-zero, basically 0 v. So then I need to show that f is not a isomorphism, right? That means injective, not injective, or surjective. But that just see from here that what is the kernel of this g. So g compose f is 0, that means, so g compose f equal to 0 v, this implies that image of f, this is contained in kernel of g, right? And this and kernel g is a proper subspace of v, because this g is not identically 0. Okay, this reason is as g not identically 0, because if g is identically 0, then this kernel g may be if 0, then kernel g is just v, equal to v, but as it is non-zero, so it must have some kernel, right? So as this is non-zero, so this implies that image of f is also a proper subspace of v, right? So this implies that f of v, if you take the whole image, that is not equal to v, that is f is not surjective. So this is not one surjective, so f is not also, so f is not bijective, and hence that is not an automorphism. Okay, so 2 implies 1 is also proved, 2 implies 2 prime, if and only if 2 prime is also done. Now let's see the other part, that 3 implies 3 prime. So here you have saying the other thing, that if you have h is non, so previously we just did here that there exists g non-zero such that if I post compose with f, that is gives 0, but in the next part is it saying that you also again have h such that f compose h is also 0, and similarly this f compose h prime is f. Okay, so that also is like saying equivalently. So in this case I can use, so I need to define 3 implies 3 prime is exactly similar as previous one, because there in this case again you can define h prime to be identity minus identity v minus h, that will simply gives you this f compose h prime equal to f, and conversely if you have h prime, existence of h prime, you can define h to be identity v minus h prime, and the same thing happens exactly. So just to see this 1 implies 3. So to deal this again, I will use this thing that not automorphism, so it is not not injective. So in this case I used surjectivity, but to see this h, so I'll use, so f is not injective, so this implies kernel of f is not equal to 0. That means it is a non-empty, non-trivial subspace of f, non-trivial subspace of v. Okay, so again just take a, so let v1 through vm be a basis of kernel f, and in this case it is non-zero, so I must have m greater equal to 1. Okay, and extend, okay, and it extends to v1 through vm plus n. Okay, so to a basis v1 through, so to a basis v1 through vm plus 1 of v. Now we can define easily this h, because I want this h should take everything to kernel. In this case, what should I define this? This f. So where this f is not taking 0, that means outside of the kernel, I should define that there h to be 0, right? So define h from v to v by f of vi. This I can just take vi, because f of vi is 0, because for 1 through m f of vi is 0. So sorry, this is h. Okay, so this is h. So previously I also g. Okay, fine. So h of vi is, simply take vi 1 less equal to I less equal to m, and otherwise you just define 0 outside of the kernel. So this is m plus 1 less equal to I less equal to m plus n. So in this case, see that this n is in just greater equal to 0. Okay, so then clearly h is not equal to 0, because this m is greater equal to 1. So then h not equal to 0, as m greater equal to 1, and f compose h of vi. This is, I know f of vi, so for 1 less equal to I less equal to m, and this is 0, because h of vi for m plus 1 through this is 0, so f of 0 is 0, so this is for m plus 1 through I less equal to m plus n. And f of vi being basis of kernel f, so this is 0. So this is totally 0 for all 1 less equal to I less equal to m plus n, and m plus v1 through vm plus 1 being a basis of v. So this implies that f compose h is identically 0 on v. So here also I define and extend linearly. Okay, so this is satisfied, and conversely I should define 3. If you have a existence of such h, such that if compose H is 0, then I should have this F is not an automorphism. Just similarly as before, I'll show that this is, so there exists H from V to V such that F compose H equal to 0. But again, F compose H equal to 0 means that kernel of image of H because if I take any V, H of V is 0, right? H of V for any V belongs to V, so that is exactly image of H, right? And this is contained in kernel of F. Now this kernel of F, okay, and what I want to show, and this H is not identically 0, right? So image of F is a non-trivial, so if and only this, and okay, not okay, so this is fine, and as H not equal to 0, so image of H is also not equal to 0. That means dimension of image of H is at least 1. So this implies kernel of F, this contains image of H, and this is contains not only 0, so how do I show? Okay, so this is not equal to 0, that means an image of H is contained in kernel of F, so that implies kernel of F is not equal to 0 because it contained. So as this implies this, and kernel of F is non-zero, that implies that F is not injective. That means F is not an automorphism. Okay, and this 3 implies 3 prime is simple, just as before, if and only if 3 prime, so similar as 2 if and only 2 prime. Just take H equal to identity of V minus H prime, and conversely H prime equal to identity of V minus H. Okay, so this is satisfied. So is this fine, like all the parts? So in this part we just show that if it is not automorphism, there exist H, G and G and H, such that if you pre-compose by 1, you will get 0, and that G is not 0. Obviously, if G is 0, then this is automatically satisfied. But to show the existence of non-trivial endomorphism of V, you need a automorphism F that taken F is not an automorphism. Whenever you have that, you can have G compose F equal to 0 and F compose H equal to 0. And similarly, if you just take the identity minus that thing, that is not clearly exactly equal to identity, because if I took my endomorphism to be identity endomorphism, then this condition is also trivially satisfied. But in this case, due to it is not an automorphism, so you have actually non-trivial G prime, such that this condition is also satisfied. Okay, so is this fine, everything?
Yes, that's fine.
Okay, so then let's go to next one. So here you have D is any arbitrary set, and F1 through Fn is like any linearly independent k valued function on the set D. That means it is just f1 through fn all are function from D to k, and k power D, you know, that is a k vector space. Addition is simply defined through the addition of the field k and also the scalar multiplication, right? And now if you take like pairwise distinct point t1 through tn in D and define your vector subspace V as just like the span by this f1 through fn, this f1 through fn being linearly independent, so V is a n dimensional subspace. And then this is equivalent that there exists an f in your vector space V such that fti equal to bi satisfied for any bi belongs to b1 through bn belongs to k, if and only if this the corresponding trivial problem that f of ti t1 through tn equal to 0 only has trivial solution, right? The question is clear, right? So in this case you have V equal to, you just define the span. So again I will just denote this span by f1, this angular notation f1 through fn. And so as linearly independence of fi, so f1 up to fn are linearly independent. This is imply that dimension of V with this k equal to n, right? And you have this t1 through tn distinct pairwise point. So then I am saying that for any b1 through bn, this belongs to k power n. So these are n tuple elements in k power n. So so there exists f belongs to V such that f of ti are also fixed, t1 through tn belongs to D fixed, f of ti equal to bi will be satisfied if and only if f of ti equal to 0 for 1 less equal to I less equal to n. So if and only if this part, this implies that f is 0. Only trivial solution. This satisfied only if f is the trivial function, like 0 function. Send everything to 0. So this is the problem. So now for this one you can just simply define a map, and again by rank nullity theorem this is actually follows. So you can define a map f from, because you are for any f in V you can define a map to a k power n, right? Because this is belongs to, you are taking ft1 f2 ftn, so you can define a map V to k power n by send like f by the k tuple ft1 ft2 up to ftn. This is clearly an element in k power n, and this is also not only just a map, it is linear, because if I take f plus g, it will add up like f plus g of t1, that is simply ft1 plus gt1, and all the way up to ftn plus gtn. But that is exactly, I can write as ft1 f2 t2 up to ftn plus gt1 up to gtn. So because that is the exactly addition in the k power n as a k vector space. Similarly the scalar multiplication. So this is not only a just a map, but it is a linear map. So Bayato is a linear map, or more precisely it is a k linear map, because both way V is a k vector space, k power n is also a k vector space, is a K linear map. And now like both the dimension of V and K power n is n. K power n has dimension n over K, V is also dimension n over K. So again, using Rank theorem, we just have seen that as whenever you have dimension of V, this domain and codomain both has same dimension. So dimension K power n equal to n. So by the Rank theorem, f is injective if and only if it is surjective, right? Injective if and only if f is surjective. But what it means f is injective? F is injective means kernel of f is 0. Kernel of f, what is kernel of f? Kernel of f consists of all those function f such that ft1, ft2, ftn are 0, right? And that is precisely this thing. So if ft1, ft2, ftn all are 0, that would imply f equal to 0. And that thing is equivalent to saying that f is surjective. F is surjective means, again, if I take any n tuple element from K power n, say b1 through bn, that is that has a pre-image. So there exists some f in V such that f of that f is this b1 through bn. That means fti equal to bi. So that is exactly this thing. So injectivity. So let me just write it in the other page. That is kernel of f equal to 0 if and only if f of V equal to K power n, and kernel of f equal to 0 means you have f of ti equal to 0 for 1 less equal to I less equal to n, imply f equal to 0, because this is kernel. So this f is in the kernel of f, capital F, and the kernel of f being 0, capital F being 0. So this is exactly will imply that f equal to 0. This thing not really good. And this is implies that for any b1 through bn belongs to K power n, there exists f belongs to V such that f of capital F of small f, this is b1 through bn, right? And f of f this is nothing but ft1 up to ftn. So this is exactly the required thing in the previous thing. So this consequence is just a consequence of the rank theorem through this defining function f. Okay, so we have similar one question, like hope this one is clear, just using the rank theorem. Similarly, we have another question, this one. Again, you can do the same thing in this case also. Like you want to define the dimension of all homomorphism from V to W as just the product of dimension of V and dimension of W. Okay, in particular, if you just took the endomorphism from V to V, that is exactly the dimension square of V. So in this case also, again, you can use the like the previous thing, previous kind of map. So V and W both are finite dimensional. So you took take a basis. So just I'm roughly writing this. Okay, so outline. Suppose V is spanned by V1 through Vn, that means dimension is n, and you define again a map from F from all homomorphism, K homomorphism from V to W to w power dimension of v is n, so I can just take w power n. So how do you define? Take any, let's say, homomorphism G, send it to Gv1 through Gvn. G being a homomorphism from like linear map from V to W, so Gv1, Gvn all are elements of W, and this W power, so this is a element of W power n. Now what is the dimension of W power n? That is the dimension of W into n, right? So dimension of W power n is dimension of W into n. That means dimension of V into n is dimension of V. So dimension of V into dimension of W. Fine. And what is the if I can show that this is an isomorphism, so that will exactly give us this. But this is indeed a isomorphism. So f is injective as f of g equal to 0 implies that g of vi equal to 0 for 1 less equal to I less equal to n, and vi is a basis of v, so this implies g is totally 0 because it is taking 0 on every basis vector. So that means this implies kernel of f is identically 0. So sorry, not this small f, capital F. So capital F, this is identically 0. And surjective, why f is surjective? Surjective means if you take any n tuple from here, so surjective as for any w1 through wn belongs to w power n, take f from v to w, or let's say g, as we are denoting by g, so take g from v to w by g of vi equal to wi. Vi is a basis, so I can just take vi to be wi. Then clearly f of g equals to w1 through wn. So this is surjective also, hence this is an isomorphism. So this implies f is an isomorphism. Obviously this is linear, so this is also linear. That's why I can say that this is isomorphism. This is linear again, like just as the previous case. It respects the addition as well as the scalar multiplication. So now f is an isomorphism, so this will imply that dimension of this space equal to dimension of this space. And dimension of this space we already have just seen, that dimension of v into w and w, so dimension of home vw, this equal to dimension of v into dimension of w, right? So again, it is just like the previous case, you have to define a map so that, and show it isomorphism, hence you get this thing. So next question, okay, we are just running out of time, so I'll just give a simple thing. How do you, so suppose you have a vector space V whose bases are given by xi, so you can, for any I indexing set capital I, so the vector space B may be infinite also, and you have a linear form, that means a map from V to your field K, and with it is satisfied that f of xi or at the basis point it is ai. Then I need to find a basis for this kernel f. So kernel f such that, as this is non-zero, so I must have again by rank nullity theorem that this kernel of f must be like one less dimension of V, right? Although it is not finite dimensional, if it is not finite dimensional, I can't use rank theorem, but in finite dimension at least I can say that the dimension of this kernel F will be exactly one less the previous one, because this is non-zero, so that means it is F is on 2. Once F is on 2 and dimension of K is like over itself, it is 1, so that's why I can say that. But in this case you can just take, like you can define Z I to be okay. So as F is non-zero, I must initially first I should take with that F not equal to 0, that means there exists some I naught belongs to I, such that F of x I naught, which is by definition a I naught, is non-zero. Okay, and once you have that, then you can define actually Z I as ai times x I naught minus a I naught xi, and calculate that f of Z I. So this defined you for like I naught equal to I naught belongs to I. Then f of Z I equal to using the linearity of that thing, it is simply ai naught minus a I naught ai, which is 0, because in k this is commutative, so this is just 0. So all the Z I, so Z I for like I naught equal to I naught, or even I naught it is also belongs to, but I just want to consider this thing belongs to I. So this set is contained in kernel of F. Okay, and then so that this is this is okay, then it is linearly independent and also span the, or spans means generates the kernel of it. Then we can say that this is the basis. So actually this indeed imply that it is a basis of kernel. So so that's how you need to you can find a basis of this kernel F, like explicitly in terms of xi and this ai. Okay, that's what the whole point of this question. Next one, okay, next one again you have to use the rank nullity theorem and play around it to get this one. And next two are again use the first one, so using first one you can prove this one, and using B you can prove actually C. So I'll just write them briefly in the PDF and I will upload it, so check it there. So is there any question now what we have discussed today, or anything else?
No, sir, no question.
Okay, so then we'll meet next week and discuss again some related question to the assignment, or this one. Okay. Okay, so
Thank you very much, sir.
okay, thank you. So we'll stop here.